today our topic is like smart antennas. Okay, so so everywhere you are seeing that like smartphones, and everywhere we often use this word as smartness and all. Okay, so in everywhere you might have seen that smartness does not come as it is, like we need to add some more features. Okay. Okay, so here in nature, see, this smartness is not, it's not something, evolved rapidly, but it has come from nature only. For example, I can say a perfect example of smart antennas, that is there in the, nature is that, for example, Tota Chinigi, okay. If you go and touch there, then it will automatically shrink, okay. There is some smartness in that, particular plant that, it is just, it is shrinking I know its leaves basically. So that is the first example I can see. When I walk through any land that I have found. And other thing is that our eyes. Okay, it's our eyes is also a kind of smart antenna basically. Okay, so our eyes you can see. So how our eyes works is, so I will tell you how I will show you some video as well. Okay, because it's afternoon session, you might have heard lunch now, and then I want to just start with some refreshing things, then we'll get into the topic basically. Okay, like eyes are, for example, we all know that our body has several parts, and also the our body function using the life force. Basically life force is there, and so life force is, but and also the all the actions, whatever duty you do, we are, it is emitting in the form of electromagnetic waves basically. Similarly, the eyes also works in the similar fashion, like how we perceive any object that we see is that, so we basically we send the electromagnetic signal to that object, and it gets reflected. Then here these are all the process will happen. So it is see the any object there, and then it will identify, and then it gets into the air. So here I am recognizing something, and my brain is to, so my brain is the smart here. Okay, so the smartness is from the brain. So eye is what is doing, like an antenna only. It is just it is transmitting some electromagnetic signal, and then it gets reflected back, and then perceiving it, and then it is giving to brain to decide which object it is. So the brain is the like a smarter object here. So it's so antenna is eyes, and the smart is brain. So smart antenna basically. It's from our human body perspective. Okay, and also one thing you all maybe appreciate, or that our body has a so many smartness in our within our body. Okay, so if you want to see, I will just show you one video. So how our body functions. Okay, it will be quite interesting. Just you can see here that it is taking photographs. That is eyes function. Okay, so here you can see artificial intelligence. You can see here so many mind reasons, artificial intelligence. So many supercomputers are working over here. Okay, and in order to make our activity smart, can you see here the respiratory system, how it function, and now the heart, it's pumping the blood basically. So when you eat, so you just to go to throat, then it comes to now the door will open. This is where digestion happens. Those digested, like whatever energy we got, it is getting circulated again to the body. Okay. This is the function of, basically typical function of our body basically. So inside our body, so how many machines are working? Smart machines basically. Okay. Okay. So thank you. So this video is to just to wake you up. So okay. So, and also there is a relationship between the smart antenna, smartness to our body as well. So we have so many smart devices as well in our body, basically. Okay. So then see when you look at the smart antennas, okay, this is how in 5G we talk in terms of, for example, massive MIMO, right? So the smart antennas will follow like this. So follow the user like this. Okay. So in traditional system, yesterday we have seen that, right? Whether you are there or not, I will just simply transmit. But whereas here, I will follow only the wherever the user is. Okay, that's how the smart antennas came into picture. So now today's the agenda is like we'll introduce the topic, then we'll see some of the smart antenna systems and the traditional like the traditional smart antenna systems which is there in the traditionally, and also the cellular radio system. So how it function, how it made us smarter, and also to cater the large number of users, and beamforming and adaptive array systems. So this was there. See, this is not a new technology basically. So this was there in the during the World War itself. Okay, I started evolving during the World War itself, because when they started working on the array, and some of the applications we will see, for example, simpler applications like biomedical applications we will see, and some 5G things. Then in order to have appreciate this topic, we'll just go through this 5G key enablers of 5G, like so how these smart antennas and smart technology like cellular radio systems and beamforming and adaptive array. So all these points, how it converges to help 5G to evolve. Okay. Then we will see quickly go through yesterday, as we have seen yesterday, simulation. Today we'll day before yesterday we have seen simulation. So today we'll see just a kind of a quick glance on the OTA testing. Okay, followed by we'll conclude. Okay. Now the come to topic, like so why we necessarily go for this smart antennas basically. So why? Because see, antenna is basically a passive device. Okay, so it does not have any smartness in it. So simply using the antenna, okay, for example, you have some purpose of, for example, let us take example of radar system, or a telecom system itself. So you are having omnidirectional antenna which equally transmit in all directions. Okay, but it's not necessarily, because it's not necessary that all the users are in all 360 directions. So what do you need to do? We have to focus the energy towards the wherever the user is. Okay, so that cannot be done within the antenna itself. But now, though we have some kind of smartness with the passive device itself, but we cannot do it in full-fledged manner. So therefore, what we have to do is we have to add some smartness to the antenna. So basically, smart antennas does not exist. It does not exist as it is as a smart antenna, but we have to add smartness to it by the help of other systems basically. So that's what we want to see, that is antenna really a smart? No. So it's a passive device. Whatever you feed in the RF like antenna port, then it will just do it accordingly. So whatever weights or whatever it may be, whatever the input we are giving, depending upon the input, it will activate. And there are some mechanisms are there. For example, mechanical based tilting systems are there in the 2G system. So how we do is that so how we do is that, so we have a tower. Okay, so we have antenna. You might have seen three tube-like kind of antennas in the tower, right? So here the antenna will be mounted on the vertically, right? But the user will be on the ground. Okay, sometimes ground and sometimes maybe in the floor. So I have to cater for both the users. So what I will do, either I have to mechanically tilt the antenna, or I can use some mechanical based tilting system. So that it's a kind of a small smartness we are introducing there. Okay, in 2G, 3G antenna itself, it has 3G antenna itself, it has evolved. And so some smartness, what I'm doing is antenna is mounted vertically, but I'm tilting my beam towards the ground direction. That is called as electrical tilting basically. Okay, so it is done with the help of mechanical thing. Okay, and if you, for example, beamforming and many things are there. So it needs enormous amount of signal passing to be done. Okay, so we cannot just like that we can steer the beam as wherever we want. We have to do enormous amount of signal passing and also backend, the so many processing unit has to be involved, and also so many active devices to be involved in order to make the antenna smart. Okay. Now, smart antenna systems, what it does is it combine the antenna array and the digital processing algorithms to make antenna smart. So, for example, why we are specifically mentioning it as antenna array, because single antenna cannot be, you cannot steer the beam with the single antenna basically. Okay. So what happens is, see, single antenna will have a broader beam width, right? Broader pattern, beam width pattern, right? So therefore, if you steer it also, you won't see much difference. If you want to do steering with the, if you can want to do steering between 40 minus 45 to plus 45, then it's, of course, it is okay. We have some elements in the literature that, you can steer the beams in the twin beam, soft split, hard split, like that we have. Okay, but if you want to steer the beam in the particular direction and for the intended purpose, some use cases does not allow, cannot be explicitly done by with the help of single antenna element. We have to necessarily go for antenna array in order to play with the beams and also make antenna smarter and smarter and smart. For example, see why we antenna array. See, antenna array evolved. Why it is evolved? Because in order to introduce smartness, without tilting the antenna, I can able to steer the beams. Unlike you have a reflector, which we need to necessarily need to rotate mechanically to steer the beams. Whereas in the planar array, we are having, for example, planar array. With the planar array itself, we can able to steer the beams. That is the smartness we are getting. And the basic smart antenna system, how it look like is, for example, you will have antenna array. Then it is for example, it is receives the signal. For example, either receives the signal or transmit the signal, and fed to the DOA, direction of arrival algorithm. Direction of arrival basically is being estimated over here. So in order to make the antenna smart, so what I have to do is, for example, some simple example I can say. In 5G, what we do is we have several methods called CSARS based beamforming technique, sounding reference signal based beamforming techniques, CSARS type 1, type 2. If you Google it, you will come to know. Okay. So what we will do is, here you will be having some UE here, and then you have antenna array here. Okay. So based on the user location, I have to steer the beam. Okay. So as we have seen in the, for example, here like this. So in order to do it, so I have to find out where is my UE is located, right? So that is that is done with the help of direction of arrival estimation basically. So therefore, what it does is, in principle, what
Sir, your voice is breaking.
Yeah, now can you hear me?
Yes, sir, yes, sir, yes, sir.
Okay. So the first step is that how it does is, even in SDR or MANET networks, you might have seen, you might have heard this. Initially we will transmit the broadcast beam, which is a broader in nature. Okay, then we will identify where is the user is. Then with the help of direction of arrival, then we will point the beam towards particular. For example, if the user is here, I am transmitting the broad beam like this. Okay. If I'm located, could I manage to find out that with the help of direction arrival estimation, then I can steer the beam towards that particular user basically. Okay. So then we are using adaptive algorithm. So there are two kind of algorithm beamforming you can use. For example, you can use switched beamforming or adaptive algorithm based beamforming. So the difference we will see later. Okay. This is basically a DSP process, digital signal processing unit. So here what it does is, see, this algorithm will run, for example, you might have heard LMS algorithm and maybe MMRC algorithm. So many other algorithms are available. So what it does is, so it will estimate the direction of arrival, and then it will calculate the weights. Yesterday itself we mentioned that, sorry, day before yesterday, last session itself, we mentioned that in order to steer the beam, what we need to do, we have to apply appropriate weight. Weight is nothing but your phase and amplitude to each individual antenna element. So by applying the weight, appropriate amplitude and phase to the each individual element of antenna array, we can steer the beam to the direction wherever we want within constraint. So it is not that see, if I want to steer the beam in this direction, I cannot do. Okay, this antenna array has a limitation that, for example, So I think 2 years ago, 3 years ago, they were talking in terms of plus minus 50 beam steering, basically plus minus 50. Now telecom operators are wanting us to do for the plus minus 60 as well. Okay, but I with some compromise. Okay, it's not that you can achieve plus minus 90. No, we can steer the beam wherever we want within the constraints. Okay, constraint means we can steer the beam, for example, plus minus 15, plus minus 30, plus minus 40, plus minus 15. Accordingly, the gain will vary. Okay, so it's not that you can arbitrarily steer the beam plus minus 40, but we have to maintain the gain as it is done for the plus minus 15. No, so there is some compromise will be done. So depending upon the steering angle, your gain will go down. Okay, that is obvious thing. Okay, then so that we will discuss later. So here this algorithm, what it does is it will apply the weight. It will calculate the direction of arrival. It apply the weights in the form of amplitude and phase. Okay, it's basically a complex number basically. Okay, it will be applied to each antenna port. Okay, so through RF chain basically. So RF transmitter chain or receiver chain. So how it does this? So you have RF chain. We have for example DAC output. So this is the algorithm. Will, output will be a DAC output, digital to analog converted output. There you have to amplify and apply to the antenna. Accordingly, they steer beams. Okay. Next we have is analogy of smart antenna system. So that we have, for example, auditory systems and the electronic systems. We will see one by one. First, auditory systems. So auditory system, see, it's again another smartness we have in our brain that, for example, you are in, for example, let us take one college student life example as well. So when the college is situated near the highway, right? When the person with the student who is sitting, in the window which is facing to the highway. Okay, so he has the two voices will be keep on coming. One is highway, the bus sounds and other things, right? The other voice is the teacher's voice. Okay, that if he is very or sometime we may hear some songs also from outside. Okay, it's up to the student to listen to either lecture or that song, or either lecture or to the any other sound that it coming in. Okay, so it is up to the student to decide which sound would like to have. Okay, for example, sometime some Arabic songs is going on, then even my kid is not listening to me. So similarly, so at that time we won't hear anything. For example, when my kid watching TV, Dora, especially Dora and some songs, Malama Arabic songs, even I shout like anything, but she don't even turn back. Okay, so because she is more focused on that particular like serial and like program or some. She is concentrating her paying attention to the particular thing. So she is not worried about interference. That is my voice basically. Similarly, the teachers student life as well. So whichever he is interested, for example, if it is an interesting subject, he will listen, or if it is a boring subject, even teacher is taking a very good, awesome class, but still he won't listen to that. He will listen to the other. So that way, so our brain has a kind of smartness that for example, here we are having two sounds basically. This is the interferer sound. This is the intended sound. Okay, by my brain will tune to that particular sound wherever is whichever is I like it. Okay, so the ear is this is kind of beam forming it is doing. Okay, that where ear is only tuned to hear from this particular beam forming. This is we call it as smart antenna system we have. Then here we are what we are doing. So here it is for example, acoustic sensor is your ear. Okay, here also what it does is see some electromagnetic signals are coming. Which signals to take, that is done by DSP processor, which is your brain basically. Okay, so that is the consideration. For this I can tell you one more example in Mahatma Gandhi's life. Okay, that how our brain was working as a perfect DSP processor. Okay, real-time example. I think I heard from somewhere. Okay, I read from somewhere like that. So Mahatma Gandhi went to a surgery. Okay, they were saying that okay, we have to give you anesthetic. Okay, you are saying the why? Because you will get a pain. No. Don't give me anesthetic. I will read a book. You do operation wherever you want. Okay. See here till the operation end, he was just reading the book. Okay. and once the operation done, then he just came out and he started, he continued to his work on his duty. So that is the one. So the how the processor is working depends upon that only. So you can pay attention to any one of the activity basically. That is the basic funda of this particular smart antenna systems. Okay, so here we can see that the two sounds are coming at different time or same time or different time delay, whatever it may be. But my ear is tuned to specialized brain is a specialized signal processor which decides that which one to be perceived, which one to be perceived sound or sound, wanted sound, which one is not to be perceived sound. That way it is, see, for example, unwanted interferer and concentrate on the one conversation at a time. Okay, this is our brain is a perfect analogy for the smart antenna system. Next is similar analogies like the same thing implemented in the real-time applications like electronic applications. Basically, here what we are doing, we have DSP processor similar to our brain, and we have a weights, so it has to be applied to the antenna elements. Then we are tuned to the wanted user basically. So that's what is the electronic system does. Okay, so here you can see that the sensors, through sensor is basically a antenna element basically. Okay, so arriving, for example, you are receiving the signal from two different directions, but you are paying attention to one particular direction. ஒண்ணு வேண்டாம், நீ போ, வேணாம் போ, கதவை போட்டு, சரி போ, sorry okay. So the signal arrives at each antenna element at a different time and time delay. Okay, but it's up to the digital signal processor and the direction of arrival. Okay, it will direction of arrival estimation, and then digital signal processor that computes the different user from the time delay. Okay, it will identify the user of intended and unwanted user. Okay, so here we have two terms. You might remember, you should please remember that later point of time we will see it. One is signal of interest, the other one is signal not of interest. So signal of interest is this, signal not of interest is this. Similarly here, signal not of interest is this, signal of interest is this. Okay, so and now, so why smart antennas are important? Okay, that we will see. So because see, there is one straightforward answer is that smart antennas, you see, you are going to mount anyway, going to mount for example, 1 feet by 10 feet antenna in the tower, right? Anyway, you're going to mount. You have that much space. So how you can make, you can add some intelligence to the antenna. You can increase the capacity as well as the range. Yes, there is the range. Okay. The next is with the help of MIMO, what we are achieving, multipath management, then mitigation of fading. So how it is really possible? This is how it is possible. For example, here you can see, for example, 1 feet by 10 feet antenna is mounted here. So you are just simply radiating in all, the entire sector basically. Okay, but whether irrespective of user is there or not, I'm simply, transmitting my power. For example, 40, if it is a 40-watt radio, for example, 4 port means 160 watts radio. I'm just, transmitting the energy, the 160 watts throughout the direction. Okay, therefore here, what is the limitation here? I'm not catering as many, I'm not, I do not have an increased capacity, and also coverage range also very much less. Coverage range is limited, and capacity I could not able to do. I could not able to enhance. Why? Because I don't expect user to come and stay in my tower and then do work whatever they want. No, it cannot be, right? So that is how in 4G itself, they implemented this beamforming technique. LTE advanced itself, but now we conventionally we call it as sophisticatedly we call it as 5G. Okay, so here what they have done, the same 160 watt radio, what it does is, okay, same 160 watt radio, what it does is, it will point the beams towards the user. Okay, here what we are achieving, the one is we are enhancing the capacity. You can see here that you are enhancing the capacity. The same scenario, we are catering more number of users, 3 more users basically. We are enhancing the capacity. Next application is range. We are increasing the range, coverage range. That is the key here. Okay, two things we are achieving over here. One is enhanced capacity. There additionally we are catering 3 users. Next is enhance the range of coverage. The third point is we are not wasting the power. Okay, whenever a user is there, I'm going to point the beam. Otherwise, I will keep silent. That's it. Okay. So here, but here, irrespective of user is there or not, I'm going to transmit my 160 watt power. That's it. So therefore, so energy wise, conserving the energy. Next is increasing the capacity by with the help of smart antennas. Third is the coverage range is getting increased. Okay. So these are all 3 things. And the multipath management. So how the multipath management happens? So when an interferer come over here, okay, so these signals, what happens is, see, it will hit on the wall. So actually there is some multipath management is involved in even in your Wi-Fi also. That's why in recent Wi-Fi autos, you see initially it was 1 antenna, then 2 antenna, now 4 antenna. Even now some routers are coming with 8 antennas. Okay, so why they are? Because in order to manage this multipath propagation, we will see in later. Okay, mitigation of fading we'll see in detail in later. Okay, these things. Okay, with the help of MIMO we are managing these two. Okay, next is that the previous are accomplished by, say, these are all accomplished by beam steering. The one particular thing is beam steering. So here what we are doing, beam steering means placing the maxima towards signal of interest. Signal of interest in the sense that the user location. Signal of interest is nothing but your user's location basically. Okay. Next is null steering. For example, some unwanted users are coming, some unwanted signals are coming. For example, I can tell you one scenario. We have faced it real time as well. When I was working in like IGTL, there, one of the complaints came from Vodafone that, so we are getting down, say site is getting down, means there is a call drop is coming around 4 to 5 p.m. between 4 to 5 p.m. evening one day. Other than that, it is working fine. Everything is good. RSS is good. Everything is good. Throughput is good. Traffic management, everything is good. Only between 4 to 5, I'm facing this issue. Then we went there and then we sat and then see if any object is there. No, nobody. So then we saw that, okay, any power line is there? No, everything is clear. Then then he was selling the 4 to 5, right? We went to that there at 4 to 5, between 4 to 5. That time only we noticed that there is a nearby some factory is there. Okay, between 4 to 5, they are just excavating. They are just removing their in terms of smoke. There's some smoke is coming out of that factory. That was degrading this basically the signal performance. So it was creating interference to the antenna. Therefore, the signal get degraded. Therefore, call drop arised. Okay, so that kind of, for example, if I am getting some degradation in particular direction, then I can what I can do very well do this by placing the beam of antenna. So beam minima, which means beam null towards that particular direction, which is signal not of interest. That particular direction, what I can do, I can just send the nulls. Okay, not the power, I mean beams. Okay, therefore I am saving the energy. I'm not spending any more energy to undesired direction basically. Okay. Now next is specially separate signals. That is done in the help of SDMA. Okay, will space division multiple access. We'll see shortly. Now, okay, so now we have seen, so far we have seen is what is a smart antenna, why we go for it, why it is important. Okay, now we are going for some kind of traditional smart antenna systems. Okay, so in it is not there is no much algorithm is involved here, but still it is a kind of smartness. In traditional cellular radio system, what we see cellular. Cellular means what? We are segregating the particular area in terms of cells, hexagon cells. Initially they proposed, for example, square, rectangular, circular, and everything. So finally they converge to this hexagon cell, because you can equally part this area into use. Here the idea is that, see, you are going to see spectrum is very much cost. Okay, you might have seen spectrum action happened, 1,70,000 crore they have collected, like that. You might have, and in US $14 billion. Verizon paid, I think, 12 to 10 to 14 billion dollars for the getting the spectrum. Similarly, news you might have heard, right? So that spectrum is quite expensive. So what we need to do, we have to reuse it. We have to increase the spectral efficiency. Spectral efficiency. So as an engineer, we have to increase the spectral efficiency. Therefore, the how the what we have to new technology to be evolved. For example, massive MIMO and all that stuff. So these stuffs came in picture of even in 2G era itself, that they decided that okay, we will reuse the frequency. For example, we will make it as a cellular approach. We will put tower in a center of each cell. Okay, then what we do is red is there, right? Red is one particular frequency carrier. So what I'm going to do, I'm going to reuse everywhere. Okay, reuse that one beyond certain distance. Okay, but the thing is, sometime what happens is sometimes we may get co-channel interference. Okay, because the power may be fluctuating here, it may be transmitting over there, then therefore this may get interference as well, but we have to ready for that. Okay, so this is the co-channel interference. Next is that, so in order to avoid that, what we are doing, see, even we can further expand this approach to making it as a small thing. So how we can do? By cell splitting, by making it as micro cells. So here the problem is that cost of installation of new base station will be high, because you have to see multiple, you have to install multiple base station instead of, see, for example, you can see the macro cell. This is called as macro cell, this is called as micro cell. Okay, micro cell, or we can say small cell. Okay, so this is instead of 6, how many we are having? Only to cover this particular area, we are having 7 cells basically, which require 7 base station. Okay, but in city and all, you might have seen, see, every building you will see towers, right? So because you have to cover, and also that is for 2 purposes. One is to give coverage to the particular area, and also to enhance the throughput basically. Okay, to enhance the user experience. Next is handoffs. It's another problem. Like handoffs means how it, what do you mean by handoff? For example, I'm for example, I will explain with this here. So I'm here, okay, in this particular cell. I'm just moving, okay, here and between this violet to red, okay, cell. Then I have to properly get handoff. Okay, that is called, the method is called, for example, you see, I have to either release here and then capture this signal, and then in order to maintain the, for example, if you are making call when you are traveling, you might have seen your phone get trained very frequently, very often, because you are getting multiple handoffs. Okay, yeah, consider the scenario. A macro cell means it's okay, but if you consider this scenario, micro cell approach, what happens? You will see multiple handoffs or handovers. Okay, in 2G terms, we used to call it as handover. Okay, in CDMA, we call it as handoffs. Okay, so multiple handoffs will happen. So what it does is your signal, your LNA will, your phone LNA will work and then receive the signal in appropriately, so that's why your phone get very much hotter. Therefore, so this also doesn't help. And the other approach is that, instead of having omnidirectional, initially, we started with the omnidirectional antenna. For example, this kind of this is actually a lightning air. Okay, but I think this is also an antenna, omnidirectional antenna. We were giving coverage to one particular cell with one antenna. Okay, there what happened is that, so you are wasting the power in all almost 70% of the direction. So because your user most probably will be there within 30% of the direction. So why to waste that one? Therefore, what they have done is sectorization. Okay, 3 sectors they formed to cover the 360-degree, 120-degree, 120-degree, 120-degree. Sectorization approach they follow. So why I'm saying all this? So how it is? You might be thinking that, okay, how it is related to smart antennas? Yes, there is a smartness is there, because so instead of using omnidirectional antenna, I am going to use directional antenna. Here, what I am achieving? So on the back end, processing. If you are handling with a single antenna, the processing unit is different. If you are handling within a single cell, we are handling multiple antennas, multiple sector-based approach. You have to have the corresponding a signal processing unit, because you are going to handle all the 3 users. You have to identify which user is from which user coming from this particular sector A, which particular user coming from sector B, which particular user coming from sector C. Ideally, the antenna is doing nothing, Just it will transmit and receive. It's a kind of transducer. That's all. But the backend, we are processing that which sector. So how we identify? We have a cell ID approach, sector ID approach, and also each has a ARFC number. So many parameters are there. So to identify the user is in which direction, basically direction of arrival of the signal. So if a user is coming, the signal is coming to here, to identify that, okay, yes, it is coming from sector B. It will identify based on the TRX, everything. Okay. So here, what the advantage we are getting is that sectoring. Okay, sectoring means it's 3 sectors we have, and here the co-channel interference is reduced, because see, you can see here. So for example, here each sector will have each carrier frequency. Therefore, you can able to control. For example, see, this is the one tower. We have 3 sectors. Okay, so if you are having here there is a. So for example, let's take these 2 cells. Okay, here there is a tower. Here there is an antenna, particularly with the, for example, F1 frequency carrier. So what I would do, so I will not transmit the F1 carrier from here. Okay, what I will do, I will place the F1 carrier towards this direction. Okay, therefore I can avoid the co-channel interference. Okay, so and the cluster size will be reduced. So for example, instead of, but here the problem is the cluster size will be reduced, and we can reduce, because see, we are avoiding this co-channel interference. Therefore, we can reduce the cluster size. Okay, because we can put multiple base station and then give better user experience to the user. But the disadvantage is that here number of channels per sector will be reduced, because instead of transmitting the single cell approach, where you will transmit multiple number of channels in all the direction. So whenever user comes, it will pick the channel and then do start conversing. But here we have to segregate among them, right? You have to segregate. For example, you have X number of channels, okay, but you have to segregate here X by 3 to each sector, right? Number of channels per sector reduced. For example, it has happened that one particular direction only the user is there, the other 2 direction you don't have a uni user. Then what happens is you are using limited user, limited thing, like you have a limited number of channels which can cater only limited number of users. So that way we are reducing. Next is handoffs within a single cell is increased, because earlier we were saying that see, handoff is between this cell to this cell. Okay, but now what is happening is within the cell itself we have intersector handover, inter-cell handover. Many things are there. Number of handoffs are increasing. Okay. Next is that so in order to see, these are all the traditional systems. Okay. Now we are going for beamforming one. So where here whether your user is there or not in particular sector, I will keep on transmitting the signal. That's all. Okay, but that's why we are going for this kind of approach, like a beamforming choices. Okay, beamforming algorithm. So beamforming is done. How it is done? With the help of smart antenna system, by means of, and for example, smart antenna system. How it is done? There is 2 kind of beams can be done. One is switched beam system. The other one is adaptive beam system, antenna systems. Okay. Here, so what it does is, see, based on the feedback control, that is very important over here. We'll see in the functional block diagram, and then it will customize the radiation pattern towards any particular user that you want to cater for. Okay. Next is main level to customize the radiation pattern, which means what? We are directing the main lobe towards the desired user and reject the interference outside the main lobe, which means I am going to send the nulls, either null or very low power, towards the unwanted user. I am going to direct my main lobe towards the desired user. Okay, this is what we have done. Now, switched beam. So these 2 approaches are there: switched beam and adaptive antenna system. The first one is switched beam. So here, what we do is, like whether user is there or not, I am going to generate these many number of beams. Okay, these many number of beams. So here, the advantage is that, so you don't have much complex algorithm involved here, because you are going to generate predefined beams in all the direction, 360-degree predefined beams, which need to apply some weights. Okay, constant weights. That's all. When base station on, You apply the weights, that's all, gone. You don't have to worry about where is, you have to only worry about the user direction of arrival, that's all. You don't have to apply, weights dynamically to steer the beam. Here, all the beams are in, predefined, and the beam directions are predefined, and then it is generated in all directions. Okay. Then here, number of fixed beam is fixed. Okay. And user base station select one of the predefined fixed beam that provides the greatest output from the desired user. So what it does is, see, predefined beams are generated. It will keep on monitoring in the each beam that if any beam, if user is falling here, coming over here, then I will get a maximum power from this beam. Okay, not from this beam, this beam. So for this, we need some kind of smart analysis system, but not that complex as that of the adaptive antenna system. That is why we call it as, see, it is very advantageous over the adaptive antenna array system, that it is less complex, relatively less complex. Okay, and it can fit in existing wireless technologies. But the problem is that beam resolution is lower. How come? For example, let us consider a case whereas the user is here in this direction. Then what happens? So here, the beam lower resolution, what do they mean is, like, you can see here, number of beams are getting overlapped here, right? Overlapped here because of the numerous number of beams are getting overlapped. Okay, so that's why you are getting lower resolution. Okay, but second problem is that, for example, if it had to happen that the user is here, it will pointing to this particular direction. Therefore, user experience also will be low. In order to avoid that, in order to avoid multiple beams getting generated and power is getting wasted. Second thing is the beam resolution is low, and for example, we may miss the user who is falling in this particular range. Therefore, we are going for adaptive beamforming. So here the simplest example is that, for example, you can see here, this is the switched beam. Okay, this is the beam I am generating in particular direction, right? When user is here, user 1 is here, interferer is here, interferer is here. So co-channel interferer is coming over a user signal. Okay, so we'll capture only this signal alone. Okay, but here we can see still we are sending some power, some amount of power to this interferer as well. Because you don't have a control over the side lobe, it is predefined, right? Whereas in the adaptive scheme, what we are doing, whenever we identify the interferer in particular direction, what we do, we'll send the null towards that. We'll say here we don't have a control over the interferer because we are still sending the some power, at least 10 dB lower than, or 10 dB lower side lobe level, but still it can receive, okay, and then get interfered. But here in adaptive system, what we are doing, we are sending the null towards the interferer. So these are all the technology. It's being used in heavily in defense basically. Now recently they adapted. See, in 5G itself, most of the technology they adapted from defense basically. Okay, so this has been there for many years in defense. Okay, so for example, radar tracking system, identifying the enemy target, and then for example, ballistic missiles. Many missiles are there, right? It will identify on the spot and it will track also. Okay, so if there you have to send the null towards the interferer, where you cannot see, for example, your radar is, for example, missile is launched, you should send null to the enemy's radar target, because it should not identify that whichever direction you are coming out. That way we use this adaptive beamforming system. So if we compare these two approach, that which one is better? Adaptive is better, because here what we are doing, adaptive is better, will give higher coverage range. Just before we have mentioned that we are not wasting the power in unwanted direction. We are only converging our power towards the desired direction. Therefore, coverage range gets increased. But switched beam, you can see conventional sectoring is the switched beam. We can cover. See here the comparison between three approaches. One is conventional sectoring. Conventional sectoring means what? You will just simply send the broad beam like this. For example, like this. This is the conventional sectoring. Okay, this is the beamforming approach. Okay, so now you can see that say here conventional approach, we can cover up to this. So by this, with the help of switched beam, we can generate predefined beams and then we can cover up to here. Okay, and even in now 5G also, in LTE also, we use these kind of approaches where we have, for example, quad beam antenna, twin beam, quad beam, so in each sector. Therefore, we can able to cover the user. Okay, increase the capacity as well. Okay, and adaptive array is like a massive MIMO. Okay, where you will only point the beam towards the desired user and point the null towards the interferer. Okay, that way you are increasing the coverage range. Okay, so there are three approaches. One, a traditional system, you have a limited coverage area. Switched beam system, you are enhancing the coverage area, but not that great. And here the point is low interference environment. Okay, the condition is low interference environment. We are getting this much coverage enhancement with the help of switched beam. And but when you look at the high interference environment, the sector based approach, it is gone. Okay, you have to necessarily reduce the power. In the inside the city, cell planning is very difficult basically. So I worked for around 3 months. Then I just simply exhausted with this cell planning basically, because you will get a lot of signals from surrounding in and around. So how do you plan which cell carrier to be there? But there are some numerous softwares are
Sir,
there which we can through which we
so
can
voice is
plan,
not
but
audible,
still
sir.
it is very hard to find that. But then we have to optimize the cell network based on the performance. That
Sir,
way,
voice is not
coverage will
audible,
increase. We
sir.
have to necessarily reduce. If you are identifying interference, then you have to reduce. Otherwise, what happens is both the cells will be affected. Then by the help of switched beam, you can enhance the coverage range. With the help of adaptive array, you can still get the whatever you are getting in the lower interference. Because here the advantage is that you are going to send the null towards the interferer, right? So therefore, you are hello, hello, hello,
Yes, sir,
hello.
you are audible.
Yeah, I'm audible. Okay. So I heard that my voice was not coming for about a minute.
Yeah, now it's okay, sir. Please proceed.
So where I left, because I was telling many things now, last 1 minute.
Just you are comparing these two.
These two, right?
Yeah.
Correct. Okay, fine. So again, I repeat. Here, the switched beam. Here we are, we are catering the desired user with a better enhanced throughput, SNR. But at the same time, we are sending some amount of power to the interferer. Whereas in the adaptive method, what we are doing, we are sending the null towards the interferer. By this way, what we are achieving? So we are. This is the comparison in respect of low interference environment, high interference environment. Okay. So low interference environment, we have sectored approach, right? Sectored approach we have shown some time back that so this is the sectored approach. Okay. So sectored approach, we cannot do any for example if interference so we can do we can send the power towards a particular direction. Sorry. So we cannot emit the pump the power beyond certain range because it will affect the other cells. Okay, so that's why we have a limited coverage for the conventional sectors. And switched beam, we are somewhat enhancing the coverage range, and adaptive array even further we are enhancing. And if you look at here these two diagrams, adaptive array coverage range does not get affected because whether if it is a low interference environment or high interference environment, does not get affected. Okay, because the thing is you are going to send null to the interferer. You are going to send the beam to the desired user. That's all. But whereas here high interference environment, you can see that conventional cell coverage range, sector coverage range is getting reduced pretty much, because I was there in the cell planning initially. I think 10, 15 years ago. That time, it is very difficult to plan for a cell within the urban city, basically. So what happens is you will see a lot of interference coming from various directions. Okay, what you have to do, you have to plan accordingly. The only obvious thing is that if you find any interference Then you have to reduce the power, reduce the power, reduce the power. Therefore, you are reducing the coverage range as well. Okay. So in order to avoid that, switched beam, we are reducing this interference to some extent. Okay. So therefore, can give some coverage. Am I audible?
Yes, yes.
Yeah. Hereafter, I will check every one slide because no, I don't know.
Okay.
Okay. So adaptive arrays, how it works is like so here we are having you know um, we are having array signal processing and processing system, same array signal processing system, in order to send the null or beam towards the desired user or unwanted user. So here the array signal processing is being done. It was as I mentioned some time back, that it was implemented in defense system very long time back. Okay, during I think after World War itself they started working implementing this, but commercially now it is being deployed. Whatever you see in technology in 5G, right? Most of the time you see that if you go back and read the literature in 70s, 60s, then it has already been implemented in defense that point of time itself. So we are just adapting for 5G, we are adapting, for example, beamforming technology, various other technology from the defense to make it commercial. Okay. And adaptive arrays has a DSP, digital signal processor. Next is ASIC based general purpose processor. Why it is required, I will tell you. Next is software based signal processing algorithms. These are all the three functions happens in the smart antennas. How it happens? See, for example, you have an antenna array, then you are receiving the signals from the UE. Okay, so what you are doing, you are receiving the signals and then you are giving it to the digital signal processor, where you identify, you will do direction of arrival estimation. Okay, next what it does is it will give that arrival estimation value data to this ASIC. Okay, so here you have a, see, these algorithms will be running in this ASIC or FPGA based processor. ASIC or FPGA based processor. What it does is it will take these inputs and then it will analyze. This algorithm is running in this, so it is basically this ASIC will be integrated with the antennas. Okay, then what it does is it will what it does is, so these softwares is running in these softwares are running in this ASIC or FPGA based processors. Okay, so then what it does is it will get the data from this DSP and then analyze it and then generate the weights according to the requirements. Okay, so that's how this adaptive array works. This is how it works. For example, you can see here the receiver. So here you can see you are receiving the signal and you get LNA will be there, and then a mixer LNA, all the process will be there. So here what do? You enhance the signal and down convert to the baseband. Okay, baseband we process intermediate frequency, right? For example, 400 megahertz, 220 megahertz, like that, right? But though RF frequencies, in terms of gigahertz, 1 gig, 2 gig, 3 gig, okay. But we process in terms of intermediate frequency, which is, for example, 200 megahertz. That's why we are doing down conversion. Then analog to digital. This is here we call it as digital down conversion. Okay. Then you are giving to this DSP. See, here you can see one input is going to direction of arrival estimation. Then it is giving to adaptive algorithm. This is running in this FPGA processor basically. Okay, processor, FPGA or ASIC based processor. The difference is that FPGA is field programmable. You can program it anytime, but ASIC is one fixed. One algorithm is running means that algorithm will run. That's all. You cannot modify it further unless you apply any license and then open it. Then, so now this algorithm, what it does, it will apply the weights. Okay, so here see the process will be like this. You are getting the signal from the user, then you are down converting using digital down conversion converter, then analog to digital conversion is happening. These data will be given to directional arrival estimation module block. Then it is giving to adaptive algorithm. Then it will apply, it will generate the weights, okay, and apply here over here. Okay, but the output signal will be, then this feedback will be given to the adaptive algorithm. It will go iteratively and then it will generate the output signal accordingly. Okay, next is this is the adaptive array system. The third one what we saw is space division multiple access. Okay, space division multiple access. So space division multiple access is among most sophisticated algorithm, because Because here what we are doing is we are using this beamforming approach to cater multiple user at a time. Okay, multiple user at a time. Okay, so and you are going to null the multiple other user as well. Okay, that's what we are going to gain from a space division multiple access. As the name suggests, what we are doing, we are going to generate multiple beams. We are going to send the data, for example, to the through one beam to the one user, the other beam to the other user. Whereas in the traditional conventional sector system, we will be sending scheduling based. In for example, GSM we use TDMA based approach scheduling, because you have only one sector, right? So user will be user data will be scheduled for each user. Okay, whereas here what we are doing, we are with the help of multiple beams, we can able to schedule the data at a time for example n number of users. Currently we are seeing some spec that 8 users, 8 user MIMO, and 7 user MIMO, 5 user MIMO, like that. Okay, which means 5 user will be catered at a time. Okay, which means 5 user anytime can cater. Okay, that's how. So it will be like this. Okay, here you can see with the help of this beam, I'm going to cater for this user. With the help of this beam, I'm going to cater for this user. Okay, the system wise it will be like this. For example, you can see here the same thing. Okay, same thing is getting received signal. Then you will have digital down conversion. Then you will have a DAC, a digital to analog conversion. Then you are giving to the beamformer algorithm, and you are running these algorithms, and then beamformer. Okay, here actually the weights are being applied, and then these see these outputs are given to beamformer 1, 2, 3. The same processor will be replicated. Okay, so here the weights are being applied. Then using the feedback signal, you will keep on iterating this till you get the desired signal. Then you are giving to this one. Okay, and before we move on, just give me 1 minute. Okay. Can you see my screen? Hello?
Yes, sir. Yes,
Can you
sir.
see? Okay, thank you. So multipath propagation, here we can see that see here see the sometime before back we have mentioned, right? So multipath propagation and fading, right? Now we will see those items. Okay, so now we have seen, let me summarize these things. Like for example, initially we started with the introduction to smart antennas, and then various the smart analog systems, and then we started with this beamforming approach, and beamforming, how it is done, two beams, switched beamforming, sorry, cellular radio system, then beamforming approach, switched beam, under which we saw switched beam and adaptive beam array, and then adaptive algorithm. Also we have seen some kind of algorithm as well as the implementation perspective, and then comparison between the conventional sectoring, switched beam, and the adaptive beamforming algorithm, and at last we saw SDMA system. Okay, now we are going to multipath propagation, and see here. So this is the basic fundamental principle for the MIMO. Okay, MIMO. We will see this multipath propagation, how it helps in the capacity enhancement. Okay, so here, see what we are doing. See, we'll have always have a, see, a tower is transmitting. We'll always have a direct signal. then you will have a multipath signal. Okay, multipath signal. So that will interfere me at any point of time, because this is the direct signal I'm getting here. This is the delayed version. It may create constructively or destructively. Okay, if it is in phase, it's fine. If it is out of phase, it will destruct my signal, right? Therefore, multiple delayed copies will come into picture. Okay, therefore, so here the co-channel interference are coming because of this. Okay, because of this, co-channel interference comes often. Okay, because user is sending very low power. Okay, minus 70 dBm or something like that. Okay, so it is getting recognized by the signal. By the time multiple copies of the signal will come into base station, it is very tedious task for the base station to analyze it, right? So therefore, we are getting so many. It can be a constructive or destructive. Okay, so how it is associated? What is the problem associated with the multipath? Is there are three problems. One is fading. Okay, next is, just a moment. Sorry, am I audible?
Yes, sir. Yes.
Yeah, thank you. Sorry for the interference. Okay, so it's also another interference. Okay, so problems associated with the multipath is that one is fading. Next is phase cancellation. How it happens? Because we are getting multiple copies, right? Which will have either in phase or out of phase quantities, right? For example, your signal is, for example, this signal is arriving at, for example, 0° phase shift, but this signal may arrive at 180° phase shift. Okay, so for this, I will just here. So how it is, see how phase and this one is important, that we will see with the help of this particular thing. See, so you might have seen sine wave, right? This can be represented in many ways, right? For example, the one sine wave corresponds to one full lambda, right? One full wavelength. Okay, so now, so this is quarter wave, lambda by 4, and this is lambda by 2. This is 3 lambda by 2. That's it. 2 lambda by 2. Okay. Sorry, 3 lambda by 2. Okay. 180 degrees. Sorry. I think 1.5, 0.75 lambda. Okay. So now, so this corresponds to what? So in phase, with the help of phase, 0°, 90°, 180°, then 360°. Here it is 270. Okay. Now, okay. So lambda, 1 lambda corresponds to 360°. Correct. 1 lambda corresponds to 360°. Okay. Now next option is, how it comes. How lambda corresponds to 360°? Because any distance, for example, if distance is d is equal to lambda, if I want to calculate the phase that is introduced by this particular signal when it travels from 1 lambda, when it travels to 1 lambda, I have to simply multiply phase constant with the this distance. Okay, if I want to find out how much phase shift it is introduced when a signal travels a distance called d, what I have to do? I have to simply multiply the k. So k is what? 2 pi by lambda. Okay, multiplied by d is 1 lambda. So lambda get cancelled. Therefore 2 pi, which is 360°. This is how we have to interpret the sine wave, right? So how it helps us in help us, correct? So how it helps us? So because see, if you are traveling, for example, 1 lambda extra, okay, which means you are introducing 360°, then it's fine, it is in phase, no problem. When you are traveling half lambda extra, you are getting straight wave signal, direct signal here, half lambda extra, what you are generating, what you are having, your signal will have same copies will be there, but one with 0°, one with 180° phase shift offset. Okay, therefore it will get the exactly opposite. Therefore, out of phase condition will come to picture. So that is how this delayed version is happening. That's how we have to interpret these two signals. One is direct signal, it has come already, right? But other signal, reflected signal, you can see it's a delayed version. Okay. Okay. So therefore, what we are doing, we are getting phase cancellation, phase fading, and delay spread, and so on. Okay. So fading. Next comes fading. So next comes fading. So fading, what you have done? So as the signals are delayed, okay, the phases of multipath signal components that combine destructively. So that is what is the over a narrow bandwidth. Okay. So when the signals are delayed, it may create destructive interference, which means destructive means, see, two signals are coming exactly opposite phase. What will happen? It will destructively, destructively combine, and then you will get the fading. Basically, the signal amplitude gets diminished. Okay? It will be reduced, leading to a fading of a received signal. This results of what is racing? For example, also known as relay fading or fast fade. Okay, the signal direction of signal strength is called as relay fading or fast fade. Next is and see fade zones. For example, you can see that you can see here the fade zones. See, some of the fade zones will be there. There you can see that because of multipath, you may get some fade zones. Nowadays network planning is done in a very advanced manner. So the fade zone they will identify it, and then they will see which path they can cater this one with the help of massive MIMO antenna. Basically, massive MIMO, one of the use cases that if the user is behind this fade zone, then how I can cater this user by making use of this multipath. Okay, in massive MIMO, what we are doing by making use of this multipath, how I can cater the user who is behind that object, means, or for example behind the building or whatever it may be. Okay. Next is phase cancellation. You can see this is what I was mentioning. This is the direct signal. The reflected signal is this one, exactly opposite phase. What will happen? Phase get cancelled, right? So therefore, then it will be dropped. It is completely dropped. Okay, that is how it happened. Next is delay spread. Yeah, this is another serious problem basically. So here, what we are happening is, see, for example, when you are getting delay, you are getting direct signal and the delayed version. For example, due to multipath, you are getting delayed version. What will happen is, see, we are scheduling a data, right? The scheduling is done in the MAC layer. Okay, layer 2 level. Okay, scheduling is done. Therefore, see, you will be expecting some data from user 1 at X point of time. But at the same time, for example, if you know simple interference, what I am getting, see, transmitted, I am receiving at multiple instead of time, chunks of data in multiple instead of time. Then I will combine these data and then extract the original information. When interference is there, if interference is not there, it's fine. I can combine and recollect the data. But whereas when interference is there, here you can see that there is a delay in this particular signal. Therefore, what will happen? What will happen? It is going beyond this one. So it is getting inter-symbol. This is called as inter-symbol interference. This is separate symbol. This is a zero symbol. This is the first symbol. So we are getting inter-symbol interference between 0 and 1. Okay. So therefore, bit error rate rises. So here when I combine, then I will get for example error only. Okay. Next is how so far we have been talking about direction of arrival, how it is done. Okay. So that is simple two examples we will see with the planar array and two element array. Okay. So here is that direction of arrival in planar array. Direction of arrival in planar array. How we are doing? I will just explain. This is the planar array. This is the object. So R1 and R2. So we are receiving the signal. Okay. So now how we calculate the time delay? So it is very simple. So it's a conventional traditional velocity formula. So the velocity, what we will say, V is equal to d by t, right? If you want to calculate t, what you have to do? T is equal to d by distance by velocity, right? Same applied here. Time delay is tau mn, and the del r is the distance, that is offset we are getting. Offset where, see, means how much it is the signal is getting due to multipath. No, it is saying longer route, right? How much offset with respect to the direct signal, how much offset I'm having? I have to del r is calculated using that. Then velocity. If you divide by velocity, you can very well calculate this time delay calculation. You can see here that del r is equal to dmn cos psi. Dmn cos psi. Dmn is nothing. Del r is equal to dmn cos psi. Okay. So dmn is nothing but your this is the distance. Okay, y cos with respect to cos psi, y cos, because psi is actually you have to interpret it as, for example, sin theta cos phi plus cos theta sin theta sin phi, because it is in spherical coordinates basically. The dmn is nothing but your m into dx square and n into dy square. This is the distance I am getting offset. This is one signal I am getting, one signal I am getting from this R2. The offset is dmn. I am calculating over this, and then you are see this cos psi, right? I am just substituting this value and then finding out these values. So cos psi, so I am simplifying and then finding out as m dx sin theta cos phi, m dx sin theta cos phi plus n dy sin theta sin phi. Hello, can you hear me?
Yes, sir. Yes, sir.
Yeah. Divided by divided by velocity. Okay, then you can calculate the time delay that has happened due to the multipath. Similarly, this is how we calculate for the planar array with the help of planar array. Okay, and for the two element array, it is very in order to have a convention. So you can see that the d cos theta we are seeing that here we are seeing d cos psi, because it is a two-dimensional. Okay, we have to use spherical coordinate system. If it is a two element, right, only two element, we are simply using d cos theta. Correct. Okay, so how cos theta is arrived? So this is the theta, and then adjacent one. This is the adjacent divided by hypotenuse. Hypotenuse is d. Okay, hypotenuse. So when you want to find out this distance, then it will be d cos theta. That's it, right? So cos theta equal to adjust this x value divided by the d. So if you want to calculate x, it will be d cos theta. Correct. So the d cos theta offset we are getting, and so here this delay depends upon the antenna geometry, whether it is rectangularly. See this antenna geometry, whether it is rectangular or square or triangular or hexagonal or circular. Okay, this offset will be dictated. And second is spacing between the elements, right? So here you can see when d changes, I'm getting, so this also gets changed. For example, from this formula you can see del r is getting changed when spacing is changed, right? Therefore, accordingly, the delay also gets changed. Okay, and next, adaptive beamforming. Here, so far we have been discussing this so many times, but just to give you an overview that. Okay, so here, so why it is important? So why we saw this one? So this is to direction of arrival is the major part of the adaptive beamforming system. Okay, so that is why we just described how we evaluate that, and then it has a DSP. Well, what it does is, based on the direction of arrival, it will generate a set of weights. Weights means what? Amplitude and phase. Amplitude and phase. Okay, these two will be done in order to place what? In order to these amplitude and these weights will be applied to the antenna array to generate the main beam towards the signal of interest, which is intended user, and while suppressing, which means sending the null towards the signal non of interest. That is what is adaptive beamforming. So here we have two kind of scenario. One is without mutual coupling. The other one is with mutual coupling. Mutual coupling means what? See, they obviously see these two elements are placed in over the same PCB board, right? So this will see obvious that these two elements will talk to each other, right? There will be some understanding with that. So, for example, similarly in our class, so some students will always talk with each other. He will never listen to our lecture, right? So that is how here also it will happen, because our lecture will become so because of that interference, they are talking to each other. He will not be able to listen intended content, right? That is how it is applicable, solely applicable in array as well. Okay, so it will talk when it talks to each other. Then the algorithm will be different. When it when it don't talk to each other, implementation is different. When it talks to each other, then I have to process the coupling between them. I have to see here. I don't have to bother about coupling between them. Here I have to bother about coupling between them. Actually, the channel matrix will become complex. So C21, C12, all the stuff I have to incorporate in the while doing this, while calculating these weights. Okay, and for example, if you see the amplitude value, so if I compare 0 is maximum value, Okay, whereas see without without coupling, you can see this is the actually better rate, I think. Without mutual coupling, you can see very decent pattern, right? When mutual coupling arises, then what is happening? You can see here that better rate is increasing. Okay, and so the mutual coupling is, so here the two purpose is there. One is two implication is there. One is, so here the two type of mutual coupling. One is radiation pattern and impediment of antenna element. Okay, for example, this is the antenna element. For example, this is the antenna element. This its radiation pattern and impedance pattern will get changed due to the coupling from these surrounding elements. Okay, surrounding elements. Okay, or change due to the vicinity of the array other elements. Vicinity of the array elements. If you are transmitting, for example, you are placing one element on the center, and surrounding of that you have many elements. This particular element radiation pattern and impedance will get affected because of the other elements. Radiation pattern and impedance of the other radiators, like for example, other radiators are also altered by presence of the original antenna, which means this is within the array. Basically, within the array, you are going to see one antenna element is going to be affected because of the vicinity of the other elements within the array. Whereas here, what we are going to get, for example, original antenna array will get affected because of the other radiators. Maybe it can be, for example, that's why defense area, they don't allow. They don't allow in different. Hello, can you hear me? Hello.
Yes, sir.
Yeah. So how much time I have more?
Sir, you can proceed, sir. No problem, sir.
Okay, 15 minutes is there.
Okay.
Okay, I will try to
No
conclude.
problem, sir.
Conclude. No problem. Thank you. Okay, thank you. I hope it's not boring. Okay. So, okay, here other editors, for example, you might have heard recent news that 5G implementation in US was affecting the airport, right? So because of these kind of issues only. So what is happening? Original antenna is getting affected because of the signals, other radiators coming from the nearby thing. That's why they stopped, implementing within 2 kilometers surrounding of the airport. They stopped implementing this N17 band, especially 3.32, 4.2 gigahertz band. They did not allow to deploy the sites there. Okay. Next is optimal beamforming can be done with the help of various methods. One is minimum mean square error, minimum signal to noise ratio, minimum variance. Many methods are there. Here, what we will do, we will have a cost function. You might have done this algorithm and all development maybe for the other image processing, something like that. The same applied here also. Here, what we are doing, we are going to see what we are going to do is we are going to have a, for example, cost function which consists of desired radiation pattern and the what pattern I'm achieving right now. Then I have to find the difference among them. Then that will be the cost function. When cost function becomes 0, which means you have achieved your desired radiation pattern, right? So there are many methods are used. One is minimum mean square error method. This is the way commonly used method in everywhere. Okay. Here what we will do is we will square the error, the cost function because the error between the desired pattern and the achieved pattern, and then find out this, and then we will apply these Wiener filters. It will be a kind of a Wiener filters to calculate. And here you can see that so error signal will be between the desired signal and the output of the signal of the array. Okay. Next is least mean square. So this is another algorithm which is widely used for many applications. So here also it is being used. Here there is no prior knowledge is not required. It's not required. So therefore, prior knowledge is not implemented. Therefore, the no memory is involved over here. Okay. So no memory is required. No matrix inversion is required. That's why it is somewhat simpler algorithm. But the problem is it does not have a prior knowledge. That's why it is a kind of a small and then not that efficient. Okay. But relatively it is better than this MMSC. Okay. So this is how the algorithm will be running. The algorithm is running. It is applying the weights based on the input signal. It is algorithm is developing calculating the weights, applying over here, and then get the YK. So here is the difference between these two signals, YK and then whatever the algorithm related signal. We are comparing this, and then this is the actually the cost function basically. Okay. And the results are like this. Okay. Signal of interest. So can you see here? When algorithm is running, when signal of non of interest, it is see how it is suppressing the signal, right? Signal of interest while while maintaining the signal of interest direction, we are suppressing the signal towards the signal non of interest. You can see here how it is, see how it is suppressing. This algorithm is running. So for example, if your algorithm is running, the results will be like this only. Okay. Yeah. Okay. Next is mobile ad hoc network. So here, this is also another important application for the smart antenna system. So here, what we do is in ad hoc network, what we'll do, each node will communicate with the other node, and it will sense the other node, and then it will start communicating with the other nodes. Where we need the smartness, right? Whether we do, see, for example, a node may be in this direction, or this direction. I have to have a smart antenna to communicate between that antenna. Okay. Here, basically, the MAC protocol only will take care of this because in these all nodes will share the L2, this MAC layer. Okay. Okay. So with the help of smart antenna, here, can you see here? See, we have several nodes here, but it is communicating to the particular node, right? Based on it will sense. Here also the same approach is used. For example, it will initially broadcast the beam and then identify where is the user. Accordingly, it will direct the beam. Right? Next, you have, for example, 3 beam, 3 nodes like that. Okay. So this is the MAC protocol thing. Like, for example, you can see here that source, it is sending to the destination. Destination is responding, and the control signal, and the source is sending the beamforming. Then destination is responding the yes, my beam is towards me, and is responding. Then data transfer starts. Okay. Then it will acknowledge, yeah, I got the data. Okay. That's how the protocol works. Okay. And some of the antennas in biomedical application as well. Magnet we have seen biomedical applications. You can see here that you are developing a capsule kind of antenna, and then you are placing inside the pig. Okay, capsule kind of antenna you are placing inside the pig, and then you can see here that in the muscles of the pig, and then you are monitoring the pig wherever it is going. Okay, you are using base station. You can able to monitor wherever this pig is going. The similar approach is being used for the, for example, truck. Actually, this logistics system, they are very much using this approach. Like they will mount the antenna, like the device in the truck. They will monitor sitting at the Delhi or anywhere in the world. They can monitor wherever is the truck. All the trucks they can monitor. Okay, and expected time also we can find out. Now 5G, I think I will quickly cover this. Okay, 5G, this we have seen covered already. So here you can see that in 5G we have massive MIMO, all that stuff. Okay, and the key enablers of 5G. I think I will quickly cover this to some of the slides. So key enablers of 5G is, one is the smart antenna systems. Okay, smart antenna systems like this, and we have many approaches are there. One of them is here, you can see that it is the unique feature, the use case that we see here, that very high speed data rate, the heterogeneous devices where using IoT, and low latency applications, like for example how it is done. See, very high we'll see one by one. Very high throughput, how we are achieving. We have a large spectrum, and also MIMO we are using, multiple access techniques, space division multiplexing we are doing, and okay, then massive MIMO along with the beamforming. So beamforming will enhance, how it enhance I will just show you. IoT. So here you can see that when the order of modulation increases, the capacity increases. So this is the network slicing. This network slicing is now very much used for the low latency applications. So how it works is, see, for example, EMBB slice means here latency is not a problem. Okay, you want to just download the data. That's all. Even 1 millisecond, 2 millisecond delay, it's also fine, no problem. Okay, so there you will have some kind of architecture. Then you have a IoT application where also delay is fine. But whereas here in this autonomous car, you can't compromise on the delay. You have to respond within a millisecond, right? So therefore, it will follow another kind of architecture. This is called as network slicing. Okay, network slicing. These are all now running in the software side. Okay, not in the hardware basically. That's why we can able to achieve very low latency. The high data rates, right? We were telling that everybody is telling that okay, 5G is giving higher data rates, How it comes? It's it starts from the fundamental Shannon's theorem, right? Capacity, operating bandwidth we are increasing. Now we are going to operate in 100 megahertz, 200 megahertz occupied bandwidth. Next is number of antennas are increasing. MIMOs are increasing 88 or 44 or 16T16 or massive MIMO and so on. Next is SNR. Yeah, this is the key point. With the help of beamforming, what we are achieving? We are getting SNR is improved. Therefore, I can able to enhance the capacity. Next is number of TX antennas we are increasing. This is and channel matrix also. Complex channel matrix algorithm we are running in order to appreciate the MIMO performance, right? So these are all the OTA testing. For example, if you want to test the beam towards a particular direction, this is for massive MIMO especially. Okay. So for example, you are steering the beam in this direction. I can able to find out. See, we have a horn. Several horn antennas are mounted here. You can able to, if you are steering the beam in this direction, I will get the maximum output over here. By that time, I can find out, okay, which direction my beam is. Okay, I can able to identify. This is called as over-the-air testing chamber. Okay, over-the-air testing chamber. Okay, this is how will be done OTA testing. So you will have a UXM. This is the emulators. Okay, then you have a channel matrix. See, for example, you will have a real-time scenario, right? Trees, buildings, and all that stuff. All that modeled as a kind of channel emulators. You have a base station emulator, channel emulator. Then you are going to test your UE. As you can test the antenna performance of the UE or anything, whole unit UE performance. So this is how we do testing. For example, how you do is like in order to measure the beam which in particular direction, we will test in this kind of environment. Okay. Yeah, I hope I'm on time. Yeah, exactly 2 minutes are there. Okay. So now, we started with the introduction of smart antennas, then various smart antenna systems, and we have seen traditional cellular systems, and then beamforming networks, and then we saw the switched beam, adaptive beam, and the SDMA based approach, and how we are achieving this adaptive beamforming with the help of in planar array, and how we use this smart antenna technology in various use cases like 5G and also the biomedical and also the various other applications. Okay, and we saw various beamforming scenario as well. Okay, and adaptive array systems, various smart antenna applications, and finally we saw application of smart antennas in 5G. Okay, and some kind of testing setups, and that's all. So thank you so much for listening to me.
Thank you, sir.
Is there any question? Okay.
Thank you. Participants, if you have any queries, kindly unmute your audio or else post your queries in the chat box.
I saw some queries were there. Is it a query or not audible thing? Oh, okay. Feedback form. I saw it.
Participants, kindly post your queries in chat box. I think since time is 4:45,
Yeah,
be
no
leaving
problem.
from college, sir. I think so, sir.
Yeah.
Thank you, sir. Thank you very much for coming here and taking the session on smart antennas. We have learned so many things, sir, like adaptive arrays, beamforming algorithms, LMS algorithms, 5G technology. Really, it will be useful for faculty members who is pursuing PhD in this line, sir. Thank you very much, sir. Thank you very much.
Thank you. Thank you so much for the opportunity and for the listeners who have spent, I think, 1.5 hours in the very hard time, basically.
Yes, sir.
Thank you so much for that.
Thank you, sir. Thank you for coming, sir. Thank you very much. Thank you, sir. Thank you.